MPL? What's MPL? Is that a class? Oh, yeah, that sounds terrible. Ooh, yeah. That sounds not fun. At least you have something enjoyable like logic in WebAssign to look forward to. It's almost as bad as WebAssign. Yeah. All right. So I posted some updated notes that include 3.3. So if you don't have those updated notes, maybe grab those or just grab the notes from at the end of class. That's what works too. I am going to bring them in here. Put them not in pre-calc, but with you guys. So of course the first part's going to be the same. And here I'm going to change this to updated 3.3. Wait, if WebAssign had 10 questions in a row that were write an expression that's equal to 1. Well, yeah. I did get a chance to look at one of those, or two of those questions. Two of those are really silly in the 10.2 homework. It's like, solve for x. There's nothing to do, but logic time. All right, let's hit it. So where did we end off? I'll have to check my notes here. Oh, that's something else here. That is something else. Oh yeah, so we talked about conjunction, disjunction, which is just and, or and respectively, and then the negation. We talked about order of operations. So what we do is we build out from inside the brackets and then work our way out. Well, I don't have anything to say about MPL. Just glad I'm not doing it. So then negation, especially, right? You want to negate the whole statement. And so you want to be really careful. And then we worked up to kind of truth values of bigger statements like this. And then we had a truth table, which we're going to do more truth tables today. So don't worry, but we have to figure out, so our truth table, we have to build up the statement to figure out when these things are true or false. Just like we ended off there. And then the next thing we had to do was the conditional, which can be not that fun, but it's okay. Math 139, 149, that's a different course. Alfie's coming back today. Or I should say Alfie came by today, or is coming by today. So, there. So what I'm gonna do, let's just skip right into the conditional. So section 3.2 continued, which is, where were we here? The conditional. Okay. I'm just gonna steal this in here and then we can talk about it. Whee! Okay, so no, Alfie's just some example from the textbook, but but the dog might come by too. So whenever we have something like if P then Q, this is what we call a conditional statement. So I'll underline that because that's kind of the definition. Okay. How we symbolize it is with an arrow, if P then Q, right? And so that's how you're going to read it. Technically, P, so whatever the first statement is, the if part of the statement, is the antecedent. And Q, which is the second part of the statement, the then part of the statement, is called the consequent, right? If this, then this. So you can think of it as a consequence. So I'll underline antecedent and consequent just in case we say it. I'll probably try to avoid saying it because I don't like all that terminology, but sometimes we need it, right? And so the statement if P then Q is a conditional statement. So I'll add that here. So the conditional is something like if P then Q. Oops, that should be Q. All right. So what happens, and this is where it gets weird, okay? The truth value for a conditional, if you have a look, so if we know the truth value for P and Q, and we've got this truth table, which is the default setup, right? True, true, false, false, true, false, true, false, right? That way we can make sure that we've covered all the different combinations. If a true statement, so if true, then true, well, that conditional statement is also true, okay? If true, then false, that's the only time that we're going to end up with a false statement, right? Because the end game was false, okay? Even if you start with a false statement, then it gives you a true statement. Well, at the end of the day, you have a true statement. So that's how I kind of remember it. And then if I say a false statement and then I follow it with a false statement, here I've kind of, I think of it as establishing kind of a false world. So then if I say another false thing, then it makes it true. At the end of the day, these, we just need to memorize them, right? So this is a rule that we need to kind of keep track of, right? Just like we should be able to develop, you know, the truth value for P and Q, right? P and Q, there has to be two values of true, right? P and Q would be true, false, 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 right? Oh, where is this coming from? It's in section 3.2, and we're just going to keep working through that section. We started it last day, but it's from the conditional. So, so these truth values, you have to remember, or as long as you kind of tell yourself, well, the only time this, or I should say, if P then Q is false, is if Q is false. Okay. So that can be, for me at least, it can be very confusing because it's not obvious to me that these would be the truth values, but they are. So let's see here. Let's make up some examples just to kind of get the hang of it, even though I don't find them that helpful. These ones, because it still is hard to think about. All right, So we're going to make up an example illustrating each of the 4 cases of the conditional. Okay, so I'm going to start with a true statement. So if true, then true. So as long as you're saying something true, then something true again, well, that would be an example. Let's just keep it nice and simple and mathy. So if 7 is less than 14, then if I add 2 to both sides, 7 plus 2 is less than 14 plus 2. Okay. Both of these things are true, and so I'm saying a true statement followed by a true statement, so of course overall it's true. The second statement, I have to start with a true statement and then follow it up with a false statement. Remember, this is the only time that the conditional is false, right? So here, if 7 plus 5 equals 12, then 7 plus 10 is 15. Right? You can kind of think of it as, okay, so if 7 plus 5 is 12, well, okay, sure. Then 7 plus 10 is 15. That's false, and so this whole statement is false, right? So that's where we can think about, so here, this is true, this is false, right, overall. And that's going to be the first and last time that we get a false statement overall. If we do, so now we're going to start with a false statement and end on a true statement. So if 7 plus 5 is 15, right, that's false, then 8 plus 2 equals 10. Because we landed on this true statement, the overall statement is true. And for me, that's not obvious. If a false statement and then a true statement, or sorry, and then followed by a false statement, we can have something like if 7 plus 5 is 25, then 7 equals 20. Yeah, so because this is true, you've landed on a true statement, right? So that's why this one is true. So even if, so you kind of disregard whatever happened first, and then if you landed on a true statement, then it's true. So now if we have this false statement, then 7 equals 20, which is also a false statement, but overall, I've established that, okay, anything goes, this is false, so I'm allowed to say something false, and that's going to be considered true. Let me see if they had a really kind of clever example here that I want to... Oh, that's not the one I was thinking about, but they have, if John gets an A on that test, then I'm a monkey's uncle, right? I'm a monkey's uncle is false, right? And John didn't get an A on the test, presumably, so that's false. But it's a true statement because yeah, if Bill Gates is trying to microchip us, then coronavirus is a hoax. That is Well, it depends. I wouldn't say some of those are statements, going back to section 1. But yeah. Well, Bill Gates is trying to microchip us. True or false? I don't know. But if we can agree on something. Okay, so Michael has typed a lot. I looked it up, and like the only justification I could find was that since the conditional is false, if and only if Q is true and Q is false, then it follows that all other statements are true. That is true, but we haven't established the if and only if yet. Yeah, this is what it is type of situation. Here. Memorize me. I'll even put in a little maybe a don't forget sticker. Whee! Cute. It's weird. It's not going to make sense. We just roll with it. Yeah. Okay, get the, oh shoot, what are those felts called? Those smelly felts. Yeah, get the smelly felts out. All right. So this is just something that we need to be able to use and recreate, right? But that's why I say the only time that this is false is if Q is false, right? So if you end up on a false statement, as long as the first statement was false or wasn't false. Now I've done it. As long as the first statement isn't false, then that's the only time that you can land on a false. Times like these, I wish these lectures weren't recorded. All right, here we go. So we made up some examples. I'm not sure they helped or not, but let's see here. Some more notes. We can rewrite this. The statement is only false if only Q is nice. Nice work, Reed. Yeah, if it starts false, then end it. If it starts false, then it's true. Pretty much. The problem is that, so Q is the only thing that really matters, except in this case, where you're going from a false to a false. Okay. Let's keep going. We'll use it, but we'll only use those truth values, so as long as we have them, committed. Okay, so the if part of a conditional doesn't have to come first, so we don't always say if P then Q. I'll need to be committed after this. Yeah. All of these statements have the same meaning, right? So if P then Q, of course, that's what we've been saying. Q if P, right? P only if Q, and all P are Q. That's weird, right? But if you're 18, then you can vote, right? So we can establish our P and our Q. So you are 18 is our P, and you can vote is our Q, right? So we can kind of highlight this here. You are 18 is our P, and then you can vote is our Q. So then if we want to write Q, if P, you can vote if you're 18. P only if Q, you are 18 only if you can vote. Okay. All P are Q, all 18, so you are 18, you have to kind of reword it a little bit. All 18-year-olds can vote. Okay. Okay. So all of those are saying the same thing. Oh, thanks, Niall, actually. I was thinking about, I'm not going to call it a test, I'm going to call it a quiz, because it's going to be kind of a written thing. Do you guys want to have it on the Monday before Remembrance Day? Do you want to have it on the 9th? I'm open to suggestions for quiz 2, which would cover, well, everything since test 1, I guess. Indifferent. Okay. So we don't have class on the Wednesday, so that's why I thought it might be nice to have like a clean break, right? So yeah, because then it would be on the Monday, which also makes it nice for a review day on the Wednesday before, because then you can review all weekend long, have our quiz on the Monday, and then be absolutely free of math on the Wednesday till the next Monday. So that might be nice. So that's why I thought the 9th might be good. All right. How about I put that at the top of the notes so people don't have to scroll through? Hey, it wasn't that far. Yikes. Quiz. We will have a quiz, and I'm only calling it a quiz because I want it to be in the quiz assignment category, but I'll kind of ride the wave, whatever looks good at the end of the term, right? But just calling it a quiz so I can put it where I want. So we will have a quiz on November 9th on, shoot, now I can't remember. Oh yeah, functions. Yeah, so because there aren't WebAssign questions for some of these, I'll probably just post a PDF for you guys, and then you'll submit your work on Gradescope. So, but you'll have the whole class time to do it. So I'm just scheduling it in that class time so that it's kind of designated and timed. So it'll be on functions, exponents and logs, and logic. Ooh. How's that sound? Okay. Bad. Bad. Okay. So I'll kind of map it out. We'll see. I'm curious to know how far we get today. I was hoping to finish logic today, but we'll see. There's a lot in this last section. So, well, we had some brief functions, but then we talked about, what was it? Oh yeah, we talked about one-to-one and onto functions, but mostly one-to-one functions, the composition of functions and inverses. So that would be new for this Mm-hmm. And then, yeah, exponential equations. And then because the logic is more, it makes sense to do written work for that as well. So that's why I'm kind of leaning that way. Okay, good. So what I'll do is at the end of today, we'll kind of see where we're at. I might throw something from chapter 4 onto that test as well, depending on how far we get next day. Because we're supposed to head into the Hindu-Arabic numeration system. Stay tuned. I have no idea. And then different numeration systems. I think that's when we talk about the Babylonian, which work in base 60. Anyways, yeah, are we using it? Yeah, you would think. I know, 60. It's, hey, nice. Yeah, anyways, we'll sit on that for a little bit. But it's like puzzles, so no worries. Can't wait. All right, so what we've decided is all of these mean the same thing. So careful, I don't know what it means. All right. Let's see here. On the next page, we have things like, actually, I can grab this whole thing. Okay. Probably butchered it. All right, so we've got these translations for the conditional. Okay. But if we have a conditional P, if P then Q, then we have these other things, the converse, the inverse, and the contrapositive. Okay, so here, the converse, the inverse, and the contrapositive. As long as we're starting with P, if P then Q. Okay. So the converse of if P then Q is if Q then P. Okay. The inverse is going to be if not P, then not Q. Okay. And then the contrapositive, if not Q, then not P. Okay. So here, if Q, then P. If not P, then not Q. If not Q, then not P. Okay. So we're going to write the converse, the inverse, and the contrapositive of this statement. And I actually had to look up what a 380Z is. So I gave you a picture. And that's important, guys. No, it's not. Pretty good looking car. 380Z. So it's a car. Yeah. So if it is a 380Z, then it is a car. Okay. So what we're going to do, we can all agree. So what we're going to do is we're going to break up this statement and establish a statement P and a statement Q, right? Because if we start with the conditional P then Q, so if P then Q, then it's going to be easy to break it down into the converse, inverse, and contrapositive. So here, I'm going to let this be P and let this be Q. And then because I can, I'm going to put it down here. Oh, now I've done it. Done. Okay. So here, let's see here. P is, it is a 380Z, and Q is, it is a car. I'm only putting those because I have the page break here, so it would be on the different page. So to write the converse, right, the converse is if Q, then P. Yeah? If it is a car, then it is a 380Z. Right? Not the same meaning, which we understand when we see these kind of simple sentences, right? But it is the converse. If it is a car, then it is a 380Z. Okay. If we have to write the inverse of this, right? Not P, then, so if not P, then not Q. If it is not a 380Z, then it is not a car. Also, not the same meaning. Yeah, car elitist. So, if it is not a 380Z, then it is not a car. That's the inverse. The contrapositive, not Q, so if not Q, then not P. So if it is not a car, then it is not a 380Z. If it is not a car, oops, then it is not a 380Z. Yeah, if you don't have a car, I don't even know how much these things are, but they look fancy and expensive. So if you don't have a car like this, you don't have a car. Well, Dodge Caravan would be a van, so then it's not a car. But also because it's not a 380Z. All right. So, where was it here? I was gonna write it out, but then I remembered it's already in the notes. So as you can see, not all these statements are equivalent in meaning, right? In fact, I would kind of argue a lot of these are not equivalent in meaning. The converse and inverse always have the same truth values. Okay, so that's going to come in handy. So the converse and the inverse are going to have the same truth values. And the contrapositive and the original statement also have the same truth values. And, oh, I guess I could have put that table in here. I'll steal that because I'll summarize it on here. Whee. Okay. So here, what we're saying is the contrapositive and the original statement have the same truth values. And the converse and the inverse always have the same truth values. So we'll start there. So the converse and the inverse, true, 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 false, false, true, true. Same truth values. So that's what we mean by the same truth values. So here, same truth values. Okay. And then the statement and the contrapositive have the same truth values. So here and here, these have the same truth values. True, true, false, false, true, 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 true. Okay. So, because of this statement having the same truth value as the contrapositive, the law of contraposition says that a conditional, so if P then Q, may always be replaced by its contrapositive without having its truth value affected, right? So the truth value of the statement or the argument is going to be the same as the original statement. So here, what I'm going to say is conditional P then Q may always be replaced by its contrapositive, which is not Q, then not P. I wouldn't say that comes up a lot, where you have to come up with that, but the fact that they have the same truth values, you could land on that just by setting up a truth table, right? So you don't have to remember that, but it's just nice to have in your back pocket. Okay, so let's do another example. So we're told to assume the following statement is true. So the overall statement is true. If P, then not Q. If you obey the law, then you will not go to jail, right? If you obey the law, so you obey the law, that's our P statement. And then you will not go to jail. So Q on its own would be you will go to jail, right? But then P, then not Q would be you will not go to jail. We're going to write the converse, the inverse, and the contrapositive of this statement, right? So here, what we have is if you obey the law, so let this be P, and then you will not go to jail. Call it not Q. This one here, it's a big mumbo jumbo. And unfortunately, your eyes are gonna get crossed looking for the T's and the F's. It's like one of those things your grandparents post on Facebook. I don't know about yours, but if you spot the A, you're a genius. It's like, it's right there. True, false, true, false. All right, so here's our statement. If P, then not Q. We're going to write the converse, the inverse, and the contrapositive. So the converse, just from up above, is if Q, then P. But here, right, our Q is taking the place with not Q, right? So, yeah, true, false. Zeros and ones, they work. So the converse is Q, if Q, then P, but remember, our Q is not Q, okay? From here, okay? So we have to be careful. We've got not Q, if not Q, then P. So, and I'll change the kind of sentence a little bit, because if you will not go to jail, that's kind of weird. So I'm going to change it a little bit. So if you do not go to jail, then you obey the law, right? So the converse says, if you do not go to jail, and I guess I should scooch this over here. Where did that Q come from? There. If you do not go to jail, then you obey the law. The inverse, remember, is if not P, then not Q, okay? But the not Q is going to be a not Q in our case. So we've got not P, then not Q. But in our case, I'm going to replace RQ with not Q. Because we want to work with this statement that we've been given. All right. Not Q, we decided was just Q, right? Or not P, so if not P, then Q. So if you do not obey the law, then you will go to jail. I'll put quotes around here. Maybe that'll make it look nicer. If you do not obey the law, then you will go to jail. Yeah, all these illegal activities. Yeah, you gotta break the law every now and then. But not log laws. All right, so finally, I know someone who got a ticket for jaywalking. I know. Weird, right? I'm not sure, actually. Half of Vernon, they're all just... I'm not sure. I'll have to get more deets, but anyways. The contrapositive. The contrapositive is if not Q, then not P. If not Q, then not P. But our Q is actually not Q. So we've got not, oops, made it negative Q, that doesn't make sense. So, or Q, then not P. Yeah, all these essays. All right, so Q, if Q, then not P. If you go to jail, then you did not obey the law, presumably past tense. If you go to jail, then you did not obey the law. All right. Converse, inverse, contrapositive. It's easier, or the only way to do it really is to translate the original statement into symbols and then rework the symbols to find the converse, inverse, contrapositive, and then retranslate those symbols into English. Yuck. Don't worry, but wait, there's more. 3.3. I guess I can bring in all of this, copy. Whee. We're going to talk about the biconditional, which is exactly what you think it is. It's the conditional that goes both ways. The implication is a special case of the biconditional, and the logical equivalence is, implication is a special case of the conditional, and the logical equivalence is a special case of the biconditional. Okay. So, in general, we've seen sort of that if P then Q and if Q then P do not have the same truth values. Necessarily, they can, but in general, that's not the case, right? So it may be the case that they have the same truth values, and so for specific instances of P and Q, in that case, if they have the same truth values, then you can write the biconditional, I don't even know how to say it. If and only if? Is that our if and only if? Yeah. If and only if. P, if and only if Q. I should put that on here. If and only if. Oops. Which you might have seen IFF, or I feel like I've used it, IFF, if and only if. Make it look like I wrote a word, or letters rather, not a word. So if and only if. So this is the biconditional, where it goes both ways. Technically, logically speaking, P, if and only if Q, is the same as if P then Q and if Q then P, right? So just keeping that in mind, and you can do the truth tables for these and establish the truth values, right? and confirm that it is the same as what we found here. In fact, maybe just as a quick exercise, let's do it here. I'll put it here. P then Q. Well, P then Q. True to true is true. True to false, that's false. False to true is true. False to false is true. True, false, true, true. Or if you've memorized the conditional table that we didn't like before, right? Then we can do it backwards, right? To figure out what Q, so if Q then P looks like. So now I'm starting on the Q side and I'm moving to the P side. This is where it gets tricky, right? Because I'm going from true to true. Okay, that's fine, that's true. I'm going from a false statement to a true statement. So that's going to be true because I landed on a true. From a true statement to a false statement, that's the only time that this thing is false, right? And then from a false statement to a true, or a false statement again makes a true statement overall. Now, if I combine these, right, to make if P then Q and if Q not then P, I can make this final column here of P then Q and Q then P. And if I'm ANDing these things together, then both of them have to be true in order for the result to be true, right? As opposed to OR, where only one of them has to be true in order to get a true result. So now I've got a true and true, that's true. False and true, that's false. True and false is false. The true and true is true, which is the same as what we found here. Right. So these are the same truth values. Okay. So that's why we're able to say that they're the same. Okay. So that's the biconditional, and so we're able to just kind of replace the arrow with a double-sided arrow and say P if and only if Q. Okay. All right. Steal these here. So the biconditional can be written in a couple of ways, right? All of these have the same meaning, right? So P if and only if Q, okay, fine, that's what we've been calling it, right? Q if and only if P, makes sense, we can switch the order. If P then Q, and conversely, well, that's what we just decided up here, right? If P then Q, and conversely, right? If Q then P, but then we can also start with if Q then P, and conversely, if P then Q, which is what we established here. Right? So they're just different ways of wording the biconditional. So we're going to rewrite the following as one statement. If a polygon has 3 sides, then it is a triangle. When did things get so simple all of a sudden? If a polygon is a triangle, then it has 3 sides. So here we're saying, okay, let's let this be polygon has 3 sides. That's our P. Then it is a triangle, let that be our Q. So what we're saying here is if P then Q, then here what we're saying, if a polygon is a triangle, if a Polygon is a triangle. Sort of Q? Maybe I'll do this. P. So Q then, oops, has 3 sides as our P. So now, P, if and only if Q, is going to be if a polygon has 3 sides, there's no if. We lose the if-then part in the if and only if. A polygon has 3 sides if and only if it is a triangle. A polygon has 3 sides if and only if it is a triangle, right? Or if you wanted to, Q if and only if P would be the same, right? Because they're interchangeable because you've got that double arrow now. Okay. A polygon is a triangle if and only if it has 3 sides. Both of those would be valid. Okay. So some definitions here. The truth set is what we've been finding, right? But the set of logical possibilities for which a given statement is true. So we only care about the true statements for the truth set. That's not going to come up a lot. What will come up a lot is a tautology. So tautology, so tautology is a logical statement which is necessarily true. So what that means is that if you end up in your truth table, you're at the last step, and you're finding that you have all truths, so it doesn't matter what you do, you cannot screw this up. You will get a true statement no matter what you put into it. That's called a tautology. So what we can do is we can do this example of is P and Q. So if P and Q, then not Q, then P. Is that a tautology? Okay. We're going to start and work our way out from, so we're going to start with just our columns of P and Q, and then we're going to build out until we have this whole thing, right? So we'll need quite a bit of room. So I'm going to start with P and Q over here on the left-hand side. And I'm going to start with my usual layout. True, true, false, false, true, false, true, false. That's always going to be the case. In fact, I found a typo in the textbook. Doesn't matter. Maybe you'll find it. So first thing I'm going to do is I'm going to figure out P and Q, right? So I'm going to deal with this P and Q nice and slow. So here I'm going to have P and Q. I'm using brackets just because it looks a little bit nicer, but you don't have to. So P and Q is only true if both values are true, right? If there's at least one false, then you're out. So true, false, false, false. Wait a second. Please stay on the line. Typo. Typo, 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 typo. And it's a big one. Here I'm all proud of finding typos in the textbook. This one I can recover from financially. So it should be P or Q, sorry. So then my truth values, of course, change here. For the or is kind of, doesn't care. At least one true for the or to be true. So true, 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 false. That looks better. So now I've dealt with this one. Okay. What I'm going to do next is I'm going to find not Q just so I can do not Q then P. Okay. So not Q is the opposite of Q. False, true, true. Okay. Not Q, then P. All right. This is where we need to memorize that conditional. The only time the conditional is false is when you go from true to false. In my mind, I'm seeing the second row in the table. So not Q, then P as its own thing. Okay, so I'm going from not Q to P. So from a false statement to a true statement, that's going to be true. From a true statement to a true statement, so far so good. That conditional is true as well. From a false statement to a false statement, that's fine, right? So that is also true. And finally, I'm going from a true statement to a false statement. That's the only time that the conditional is false. So there. Now, right, I'm going from this P or Q. So if this, then this. So it's another conditional that I need to do, right? So you want to just keep your kind of wits about you here. I'll put a green box around this and, I don't know, purple box around this. So then here, my final statement, P or Q, then not Q, then P. Okay. This is my green one. This is my purple one. Be really careful. So we're starting in the green one and going to the purple one. True to true. So isn't it P? I know, but that's the typo that I found. And it's a big one. It's P or Q. So you'll want to fix that. That's a big typo that I made. Just give me 1 second. We had some doggy drama last night. She was puking all night. And I don't know what's wrong with her, but now she's being weird, and I had to call Jared to help settle her down. Anyways, she's a weirdo to begin with, so. Oh, now she's over here, but yeah. Okay, so we're starting in the green one and going to the purple one, right? Yeah, all night. It was exhausting. The Ken thing. Oh, Ken. True to true. Okay, that's true. True to true. All right. Hey, I'm sensing a theme here. True to true is true. False to false even is true. It's a tautology. All true. Oops. Therefore, this is a tautology. So no matter what the truth value is for P and Q, you're always going to end up with a true statement here. Yeah. Good. So, I'm going to copy all of this. Okay. So, if a conditional is a tautology, which is what we just found here, right? We've got a conditional statement overall, and we just decided it was a tautology, then it's called an implication. Okay. So it's an implication, and it's symbolized by, oh, that's a mistake too. It should be double arrow, and same thing here. I thought I fixed that actually. Okay. So the implication is kind of the thicker arrow, okay? And you're going to read it as implies. So what we just found is that P and Q implies not Q, then P. So the implication is a special case of the conditional. The implication is a special case of the conditional. Maybe I'll. Right, where it is a tautology. We already looked at the biconditional statement, if and only if. So a biconditional statement, P if and only if Q, that is also a tautology, is a logical equivalence. Okay. So, which you write, P is logically equivalent to Q with these double biconditional arrows. So logical equivalence is a special case of the biconditional. So a biconditional statement that is also a tautology is by definition a logical equivalence. P is logically equivalent to Q. Okay. So now, all these little, it's a lot of work, these things here, right? And they're so subtle here. Anyways, we're going to show that if P then Q is logically equivalent to not P and not Q. Okay. Good thing we don't have to translate these to English sentences. Ugh. If Alfie came by last night, then he picked up his money is logically equivalent to, here we go. Oh, the negation. Oh, what a mess. And we don't have De Morgan's laws quite yet. We'll know how to deal with this in just a little bit. Yeah, yeah. Mm-hmm. All right. So we're going to show that these two things are logically equivalent. So again, you start with your default P and Q column. So P, true, true, false, false, true, false, true, false. Okay. Building out here, if I start with P then Q, so if P then Q, we've kind of memorized what this truth column looks like, right? Assuming that you have this layout over here for P and Q, which you always should. It should always be the same. P then Q, true, false. Oops, that false looks like a true. We've all tried it. Little part marks for true, false. False going to true gives me true, and false going to false gives me true. So I'm going to deal with not Q, and then I'm going to AND it with P, if that makes sense. And then I'm going to negate that, right? So I'm going to work my way out. So I'm going to find not Q, which is false, true, and then P and not Q. Treat that as one thing. P and not Q is only going to be true if both of them are true. All right. So we've got true and false, that's false. True and true is true. False and false is false. False and true is false. If I negate this, right, because that's what I need here, I need to negate that column. So not P and not Q. True, false, true, true. So what we're finding, so what we're checking here is we've got P then Q, so that'll use my green one here. And then my purple one, not, oops, not Q then P. I need to show that not only is this biconditional, which it looks like it is, right? True to true, false to false, true to true, true to true. But when I do the conditional in either direction, right? It has to be a true statement. So true to true is true, false to false is true. True to true is false. That'll mess with your head. True to true is true, and true to true is true. Someone needs to auto-tune this. True to true. Okay, so here we go. I've got my, kind of need to squeeze this, but here we go. P then Q, if and only if. Notice that it's only one, right? So we haven't established that it's a tautology yet. Yeah, P, Q, true and false, they've lost all meaning. And then not P and not Q is that purple one. This is my green one, if that helps. Okay, but what I find is that true goes to true, false goes to false, which makes a true statement, and true and true. So now, since this is a tautology, right, all the values are true, then we have logical equivalence, right? So that means that we can replace this biconditional arrow with the logically equivalent arrow. Okay. So since we have found a tautology, oops, tautology, I'd love to know the etymology of tautology. Taut must be some sort of true, no? Step away from the etymology. Origins of words. Since we have found a tautology, we can replace the biconditional with the logically equivalent, right? And conclude, I'm going to cheat a little bit and say these statements are logically equivalent, because I don't want to write them out again. These statements are logically equivalent. Is that good, Dermot? Good. Okay. One more page, and then we'll be done with logic. Well, you're never done with logic. Awesome. But it won't be such a pain in your butt. Well, maybe at the final, but I can't remember who asked what the worst or what the hardest section of the course is. And I did say logic, and here we are. So it's gonna get better, I think. Maybe it's not a statement. It will get better. True, false, not a statement. Oh, Toto is same. Logos, word, thought, principle, speech. Thanks, Zach. I didn't know Toto meant, or Toto meant same. Something new. Something new every day. Every dang day. All right. So the laws of logic, we know the law of double negation, right? We can replace the, we just said, well, we can use the double negative of P and just replace it with P. But in fact, what we have is it's a tautology with P, and so we can have a logical implication or a logical equivalence here. I'll copy this whole section because there's not a lot going on. Whee! Oh, that got big. Anyways, that's probably good. So the law of double negation, right? So now we've got this logical equivalence, logically equivalent, which we know already, right? That if I have a double negative, that's logically equivalent to the statement on its own, right? There's also the law of contraposition. Remember at the beginning of this class, we said, okay, well, a conditional statement, if P then Q, has the same truth values as the contrapositive, right? And so here, this is the contrapositive. Contrapositive is logically equivalent to the original statement, or the original conditional. What kind of logic is this? Einstein did come up, actually. Galileo, what was that little Einstein blurb? They have all these fun, like, little fun facts throughout the textbook. Anyways, I'll read it for next day. Yeah, of course, Einstein had something to do with it. But, oh, well, that's a really good guess, Dermot. Like, oh yeah, Einstein did do something. He contributed something, of course. It's a good guess. But it's also true. Okay, so here's the contrapositive is logically equivalent to the original conditional, right? So now we're just able to replace those statements with these logic symbols. So now we've actually seen De Morgan's laws in chapter 2. Chapter 2 was when we were doing sets. So, and of course, there's a lot of kind of stuff that comes back from sets in logic. They're very intertwined. Okay, so De Morgan's laws says that, and here's where I was saying, okay, we haven't actually figured out how to break out this negation inside the brackets yet, but here we go. So if I want to negate P or Q, that's logically equivalent to not P and not Q. So notice how it switches from or to and when you break out those brackets. Same thing in the reverse, right? If I have P and Q and the negation of it, if I break out those brackets, right, meaning I'm trying to bring in this negation inside, what happens is my and switches to an or, but I can replace the not P or not Q. So these are going to be very useful. Okay, so we need these in order to expand the brackets. Expand the brackets after a negation. Maybe I should put another one. Don't forget. Oh. That sticker is turning out to be very useful today. Okay. So let's see here. Let's negate some, wait, what happened to the fast fun facts, or yeah, the little fun facts? The FFFs? Fast fun facts. I know these, well, this would definitely be an LFF, a little fun fact. But I love the fast fun fact. All right, so let's negate some compound statements, shall we? Ooh. I know, it's been too long for an LFF. I'll throw one your way and just, I'll see if I can come up with one. An LFF. Let's do here. So the negation of a compound statement is not just a single statement, right? It's something that's been joined together with a conditional or a conjunctive or a disjunctive and or that kind of thing. So if we have to write the negation of these compound statements, first one, John went to work or he went to bed. What a decision. And here's Alfie. Second statement, Alfie didn't come by last night and didn't pick up his money. So I added the by because otherwise it gets weird, but we'll do that one in just a sec. All right, so we have to negate these compound statements. We often just want to make it the opposite, but that's not necessarily what negating means. So the first one, if we have John went to work or he went to bed. Oops, I wanted to write it all lofty, but then he went to bed. Okay, so what I'm going to do is I'm going to replace John went to work, or maybe I'll say went to work is my P, or he went to work or went to bed, which is my Q. Okay. So what I have, right, is P or Q. So what we want to do is we want to negate P or Q. So I want to negate P or Q, but if I write this out, it becomes not P and not Q, right? Using De Morgan's laws, which we just had up here. Oops. P or Q, the negation of it, not P and not Q. Okay, so in words then, John did not go to work and he did not go to bed. Did neither of those things. Okay. So in words, the negation of this thing is John did not go to work and he did not go to bed. Mm-hmm. Exactly. I think, yeah, it was last class that we were trying to, or we were wanting to negate something like this, but we didn't have the tools to spread that negation out across. So now we do. Now we could go back to it, but I don't remember where it was. so it's okay. Maybe it had something to do with Alfie. Yeah, Alfie finally came by and picked up his money. No, well, we'll see. Alfie didn't come by last night and didn't pick up his money. All right, here we go. You know what, instead of writing this out again, one thing that I'm gonna do is this statement is already a negated statement. Alfie didn't come by last night. Okay? So I'm gonna call this not P. Okay. And didn't pick up his money is also a negation, not Q. So instead of confusing myself and talking about P, Alfie came by last night, and Q, Alfie picked up his money, it's easier because what we have to do is we have to negate not P and not Q. Okay? So what we're gonna do is we're gonna negate, negate this thing. So I want to find the negation of not P and not Q. Okay. Using De Morgan's laws, this is the same as saying not P or not Q, right? Treating not P and not Q as one thing. Again, like we did before. So not P is P, and not Q is Q. So P and Q, bada bing, bada boom, P or Q. I think I used, oh. So then the word negation, P or Q. Alfie came by last night. Or he picked up his money. Or he picked up his money. Okay. It. So negation isn't always what you want it to be. It could be, why not both? You can do both, Alfie. I know, I'll have to incorporate Alfie some more. Let's see what I can do. All right. There are some other operators. This is just for reference, really, in case you need it. On a test, I really feel like, unless we do something like this, which we'll finish off with, where I give you both of them and I say, hey, are these things logically equivalent? Then you should be able to show that. But don't worry about memorizing these. They're just for reference, right? And so we can build other operators in terms of our previous operators, right? Conditionals and or negations. So you can use this for reference. Not tested. Right. You might need it on an assignment or something like that, but when the clock's ticking, no, don't worry about these or coming up with these. If you have a statement like either P or Q, that would translate to P or Q and not P and Q. Ooh. Neither P nor Q is the negation of P or Q. That's okay. P unless Q, not Q, If not Q, then P. P unless Q. P because, that's kind of a cool one, right? P because Q, so P and Q, if Q, then P is how you would translate P because Q. No P is Q. If P, then not Q. Anyways, so these are just logically how you would translate some of these common other operators that we're not going to dive into, right? But I actually think the P because Q is kind of the coolest looking one. So show that the statement P because Q is logically equivalent to conjunction P and Q. Okay. So what we have is, okay, well, logically equivalent, that means we have to have a biconditional tautology, right? So this is a biconditional tautology, is what that means. So if I start here with PQ, then I can figure out what this thing is, or you can jump right to it and use it if you wanted to. But I thought it might be a nice exercise to develop this, right? So PQ, true, true, false, false, true, false, true, false. P and Q, I could start there. P and Q. Well, both of them have to be true in order for this thing to be true. And so the only time that this thing is true is the first time. True, false, false, false. Okay. So now we've got the P and Q, which is the conjunction. And now I'm going to develop P because Q. P and Q I've already got, actually. So I need another column of Q, then P. Q, then P. Looks like, okay, so I'm going from Q to P. So I'm starting at a true and I'm landing on a true. That's true. A false going to a true is still true. A true going to a false is false, and a false going to a false is true. Okay. Okay, so I've got P and Q. I've got if Q, then P. Now I need to find these two together. And so I've got P and Q, and Q, then P. Okay, that's just this column and this column. So I've got true, false, false, false. So now, what happens next? Okay, so now I've got because here, P and Q, and if Q, then P. Okay, so this is because, and this is the conjunction. Okay. I want to show that the biconditional is true, meaning that they have the same truth values, right? In this case, true and true, false and false, false and false, false and false, right? And so that's the if and only if scenario, right? So therefore, we get because, so P and Q has the same truth values as because, which is P and Q, and, oh no, I need more space here. P and Q, then P. Ugh. Yeah. So because this conditional is true both ways, same with false to false, which is the rest of them, these are true, true, true. So what I'll say is, since the biconditional is a tautology, they are, skipping some words, they are logically equivalent. So we can replace this with a double equals. Like that. Okay. How's it feel? Done logic. Celebrate. Maybe. Or maybe you like it. If you like logic, then we're done logic. It does get out of hand real quick. But, so that's where we're gonna end for the logic section. Yeah. If you like logic and tautologies, getting caught in the rain. Pina-collogics, that is really good. Getting caught in the pain, that works too. I sense a collab going on here. It's the makings of something good. If you can work the conditionals in there. Yeah. We should make a song for every chapter. Submitting homework assignments at midnight. Is it in the dunes of the Cape? No. It is? I don't know. Or maybe that's just like a young version of me singing it like that. Yeah, when, where? Well, in Zoom probably. Yeah. I'll take it away. All night long. All right. Oh yeah, dance. I don't even let you guys stretch. I'm assuming you're able to kind of stretch yourselves. All right. Are there any questions, or are you ready for math this week to be over? I am. Over, over, over. Now it's nap time. Yeah. I don't want to wait for this night to be over. You guys are picking some pretty good tunes. All right, I should stop the recording. That would be good.